We're very lucky today to have Jim Luedtke from Wisconsin University visit us and give the CAM talk. Jim, after finishing his PhD at Georgia Tech, came to IBM for a year as a postdoc when I was there, and resisted all the temptation to stay with us, and moved on to Wisconsin, and he's been there since. He's a professor there now. Jim has done a lot of work, very significant work on integer programming and stochastic integer programming, and he will share some of his recent results today with us.
Okay.
Thank you.
Thank you very much for the invitation. It's been nice meeting many of you today, so it's been really fun to be here. And thank you all for taking an hour away from the beautiful weather to be here. Hope you learned something from this. So it's a long title, basically I'm going to kind of go reverse order by first of all telling you what stochastic integer programming is in case you're not familiar, then tell you about just kind of at a rough level what that type of method is, these branch and cut methods, and then if there's time, some of the work I've been doing to contribute to improving those methods. And the works that I would talk about today specifically are with my recently graduated student, Rui Chen, who's now a postdoc at actually Cornell Tech over there. Okay, so let's get into just discussing what is this class of problems, stochastic integer programming. And I want to start with an example, and I think it's a good idea to start with an example. People always ask me, like, just people I meet in the neighborhood, like other parents and friends, what do you do? And professor, what do you do? And like, I do mathematical optimization. And they look at me with these glazed eye look and no idea. And then I say, here's an example of what I might do, even though it's only one small thing, but it always makes it more clear. So here's an example. So let's think about the power grid. Okay, so a big problem there, if you're sort of doing long-term planning in the power grid, is deciding generation capacity, right? So where should I build power generators, maybe also even power lines to connect things together so that you can sort of meet your needs that are growing over time. And so you want to do this, the way you might think of this problem is you might have some candidate generators, so they're in possible location, and maybe their size, and maybe some candidate transmission lines. And so you're trying to decide which of these to open to minimize the cost of sort of doing that capacity expansion. Is a big investment to build these things, but also to there's the cost of operating the system over time once you have those installed. And so this problem, I use this as a motivating example because it has two features in it that are significant in this class of problems. One is discrete decisions. So I'm either given these candidate locations of generators, I'm building it or not, and that's really maybe there's a little bit of sizing, but more significant is whether I do it or not, discrete. Certainly transmission lines are discrete, it's either there or not. And then there's also a huge uncertainty, right? So if I'm installing wind turbines as some of my capacity, then on any given day it's very variable and random, how much power I'm going to get out of that, right? And also, of course, demand, how much growth there's going to be over time is uncertain as well. So that's the type of problem that sort of motivates this. But I want to start thinking about how might we build an optimization model to model this type of problem. I'm going to start with the deterministic model. Okay, so just to get some notation set, and then we'll see how you might think about a stochastic version of this. And so, this is going to be a simplified version. First of all, I'm just going to ignore transmission. And this is, by the way, this is much more simplified than the real power problems. It's just meant to be an example to get you thinking about how these things work. And so, in this problem, we'll have some candidate generators, some demand locations. We'll assume that if I build a generator, there's a certain fixed cost for building that, and they give me some capacity of how much power I can produce. In my demand locations, I have some, for now, known demand. That's they call it load in energy systems. And then my decision variables are going to be for each generator, I'll have a binary variable, so it's 0 or 1, to encode whether or not I build that generator. So those are discrete decisions. But then I'm going to also have some continuous decisions. So once I've decided which generators I have open, I have to sort of allocate its capacity towards my customers. So Yij will be variables kind of sending electricity from generators to customers. And then maybe it's too expensive in some particular demand scenarios. I might not always meet all the demand, so I'll have variable Zj for like some unmet demand to make sure I can always kind of do this. And so you can then write an optimization model where I'm going to be minimizing this function of my decision variable, so that records all the fixed costs, that records the cost of sort of the variable cost of meeting some customer load from a particular generator. And this, in case I don't meet all the customer's demands, I have to pay a penalty for some amount of unmet demand. So that would be the third term there. And then I have these constraints here, which would say for every customer, the total amount of either sort of what I serve or what I declare as unmet should be equal to its demand. And then I have some upper bounds on how much I can send from each individual sort of generator, given its capacity, and whether or not I open it. So if I don't open it, that's a 0. I'm not sending anything from that generator. Otherwise, I have the upper bound of CI. So the details of this aren't so important, just to sort of say, okay, we can encode this sort of realistic problem in this optimization model where I have some discrete decisions and some continuous decisions. Okay? So what about uncertainty? So that's the next step I would do, is to build towards this class of stochastic integer programs. So how are we going to consider, handle the situation where either the demands are random or the capacity is random? And that would be the case, for example, if you're thinking about installing renewable energy, right? Then it's sort of capacity. You can think of that as random. And so in this case, the framework we're going to generally think about here is a two-stage stochastic optimization framework, where I'm going to have some decisions that I must make here and now, or the first stage, that I have to choose those and fix those before I realize I see the observed uncertainty. So think of that in the case of this power sort of planning problem as deciding which generators I install or which transmission lines I build. But those are long-term decisions. You have to fix that. It's not like I can change that day to day. And then the way we think of this is we imagine that we're going to observe an outcome of the random variables. So pick up, some day, some time from now, I'm going to see, even in a particular hour of a day, this is how much power I'm getting from all those renewable sources. This is all my demands. So I observe those things, and then I make some additional decisions in response to that, and given what I decided in the first stage in terms of my sort of network design, to sort of operate my system kind of in the best way possible. Okay? So that's like the framework that how we think about these types of problems. And so then our goal is to choose, really we care about making good first stage decisions. That's the output of this model, is this design. But we want to do that in a way that minimizes whatever immediate costs there might be to that, like to build all these generators, it has costs, plus, and here we'll say the expected value, so we're averaging over all the possible outcomes I might see in this random observations of my best response that I make when I make those recourse decisions. Okay? So here I'm saying expected value. I do lots of research on other types of measures of considering uncertainty. You can do risk measures and be risk averse, but most of I'm going to ignore that for today. But kind of the methodologies I'll talk about might extend to those other cases as well. Okay, so in order to take a deterministic optimization model and kind of make a two-stage stochastic optimization model out of that, what you need to do is kind of make this key distinction of which decisions have to be made before the uncertain outcomes and which ones can wait and see, right? And so going back to the example here, if I want to make a stochastic model of this kind of capacity expansion problem, now I'm going to have some new notation, so I'm going to assume the loads at different customers is random, and the capacity of the things that I build is random. I'm going to have sort of the same notation for my decision variables, but now I'm sort of differentiating that opening generators, that's like a long-term decision, so that I have to do here and now. But the sort of assignment of, how I use that capacity to meet my customer demands, that I do kind of in real time as I observe what's really happening. So those are going to be my recourse decisions in this model. And so then the way we would write down this model is going to be something that looks like this. So I'm going to have my decisions still are the main decisions I'm making is the binary decisions of whether or not I say open or not, build or not a given generator. I have my immediate costs of doing that. And then I'm going to add to that the expected value of, this is a function that, I'll explain in a second here, but basically this function is saying that's the best response, that I can make, given that I, made that decision X as my design choices, and I observed, these particular outcomes for the demands and the capacity. And so that function that goes on the inside here, so this expected value over those demands and those capacities, for a given value of the demands and capacities, that's the value function of this optimization model. It's the optimal value that I get if I plug in those demands and those capacities and I just minimize the cost to do those recourse actions. And so that's an example of this sort of two-stage stochastic optimization model where I have these integer variables and these two stages. Any questions about that model? Because it'd be really good if people are with me at this level and kind of understand that for just having motivation for the rest of things. Yeah?
So the CIJs and PJs are deterministic.
Oh yeah, so in the way I wrote this, the costs here are deterministic. In general, they might be random as well. And then I'll write a general model in the next one where sort of any of the data might be random, but in this case it's just those. Okay, so the general model, so this is like the two-stage stochastic mixed integer program in the general form. We're going to have some vector decision variables x in the first stage. Some of them might be continuous variables, some of them might be integer constrained. That's why I sort of break it out in those two cases. We'll say we have some linear constraints on what I can do in terms of those variables. I'm minimizing my immediate costs of those variables plus the expected value of the future. And so now I'm using this C to represent the randomness. And this, in this case, is it could be all the data that shows up in the sort of recourse problem, the general version of this. And so it could be the Q is the objective function, the H is the right-hand side, and then there's these matrices that show up in the constraints. They link together the first stage variables and the second stage variables. And so this is just kind of a more general abstraction of that example that I presented there in terms of this generation capacity. Okay. Okay, so that's the class of stochastic mixed integer program. Just to kind of convince you, there's many example applications of this, right? Basically, discrete decisions are everywhere, uncertainty is everywhere, so it's easy to come up with examples of applications of this. And so one, a big one is stochastic unit commitment that a lot of people have studied. Again, in the energy sort of world, where you have sort of random maybe loads and renewable energy production. In this case, the decisions are more complicated. You're making a whole plan of when to turn on and off units over, like, say, the next week at an hourly basis. Right? That might be what you might be looking to design. And then, given that fixed plan, which maybe you give to the operator to say, have your units on and off during these times so it's ready. But then, on an hourly basis, as you're actually sort of seeing what really is happening, you're allowed to sort of choose the production amounts in response to the demands and how much actual energy you've gotten from those renewables. Another application that I really like a lot by Louis Taimo and his co-authors was this wildfire initial response planning. And so the idea here is kind of in the first stage, what you're doing is you're trying to position sort of equipment in, this was in Texas, to that could help fight a fire. And a very important sort of aspect in fighting fires is the initial response. If a fire breaks out because there was some lightning or something, if they can get to it right away and contain it, they sort of keep it from getting out of control, right? So there's this initial response, but you can imagine that you really need the equipment to be in the right place to have a chance to do that, right? And so you have this random fire sizes that's going to happen. Your first stage decision is to pre-position that equipment, and then in the second stage you sort of see, oh, a fire started, and then you do your best to try to, sort of respond to it, right? So that's kind of a nice application of this. All kinds of logistics problems can fit into this framework, so you can think about a stochastic vehicle routing problem. This is a version known as a priori routing. So the idea there is you decide on a route that a truck is going to travel, maybe picking stuff up at customers, and then, but you don't know for sure how much stuff you're going to have to pick up at those customers. And so at some point, maybe the truck, fills up, right? And that would be kind of a bad outcome. So there's uncertainty there. So your first safe decision in that case is to sort of plan this route. But then in case, the truck fills up and you're not able to sort of fully follow that route, you have to make some recourse action of how do you respond to that. So many sort of examples there. Okay. So I'm really a computational optimizer. I'm interested in figuring out how to solve hard problems. And so, this, is sort of a dream for me because it's an especially hard problem in the sense that it combines the challenges that you see both in stochastic programming and integer programming, which are sort of two fields that are already hard by themselves. So in stochastic programming, one of the key challenges there, I wrote down this model and I wrote expected value with respect to these random outcomes. That should ring alarm bells, right? You have this expected value. Even if I have a candidate solution, how do I evaluate how good is that solution is evaluating expected value? And so that's hard to do in general. So what we often resort to is some kind of sample approximation. There's a whole field of study on that I'm not really going to get into. But that can work pretty well depending on the context. But still, even if you use the sample approximation, what you then have is a problem that you probably maybe need a large number of scenarios in your sample approximation to get a reasonable sort of approximation. And so, it's still a very large scale problem at least, right? Even if you somehow approximated that expectation. So the huge size is an issue. And then in integer programming, basically, it's just sort of the classic problem of, if you have a lot of discrete options, right? Imagine I have 100 different generators, I'm deciding I'm going to build it or not. There's 2 to 100 possible, options. So filtering through that, you need methods that, don't enumerate. You have to filter through that smartly. And so, we talk about sort of branch and bound methods, you work on linear programming relaxations and things like that, but a challenge that comes in then is, oftentimes a formulation might write down might have a weak relaxation, right? And it's specifically, combining these two things together in stochastic integer programming, that's a common sort of challenge that arises. Okay, so that's kind of the intro to what is stochastic integer programming. And now I'm going to transition to the second part of this, is working backwards in the title to talk to you about what's like the Bender's branch and cut algorithm. Okay, so that's the approach that I'm going to try to sort of hopefully talk about some contributions we've made to that, but we need to first talk about that. So let me talk about this notion of Bender's decomposition for solving this class of problems. So the first thing we've done is we've taken our random things that are happening, and we've done some kind of, say, sample approximation. So I don't have to worry about expected values anymore. All I'm doing is a sum over these scenarios. Okay, so that's going to be the rest of my talk, is just finite sums. And so I'm going to have, S is going to be the index for my scenarios, so I have a number of those. You think of that as maybe pretty large, maybe in the thousands to get a good approximation. And so now I can write down my stochastic mixed integer program using a sum instead of an expectation. So that's all I'm really doing here. This is, this was expected value before, now it's just this sample average. And everything else is kind of the same as I had before. Okay, so the first thing, if you ever want to try to solve a stochastic mixed integer program, the very first thing you should do is not look up any of my papers, because there's an easier option that often works, and that's the first thing you should try. It's something known as the extensive form or the deterministic equivalent problem. And so what you will do, given that you have these finitely many scenarios, maybe just step back here a second to the formulation. What we're doing here, remember there's these variables x, which are the key things you want. That's what you decide the here and now decisions. And then for every scenario S, there's this subproblem that says, okay, this is what I would do if I'm in scenario S. So what I can do is kind of think about creating a version of this model that just says, well, why don't I just put into my optimization model a set of decision variables that says, okay, if scenario S is the one that happens, then I'm going to do that, right? And so if I do that, that's exactly what you get in terms of this extensive form, right? So for every scenario, I explicitly introduce a whole vector of variables ys that says, okay, this is the recourse actions I'm going to take if we end up in scenario S. And then what I can do is all of those constraints that link together my first state decisions and those recourse decisions, I just write them down, repeating for every scenario. And I have my first state constraints. And so this becomes an overall formulation of this problem that's just a mixed integer program. It's no longer, that's why it's called a deterministic equivalent, because this is something you can give to your favorite integer programming solver and say, can you please solve that? Okay, so this is the first thing you should always try. And the advantages of that is it's fairly straightforward to implement. If you can implement the deterministic version of your model, there's kind of a formulaic way to sort of make an implementation that is this equivalent form of the stochastic problem. You just give this to your favorite MIP solver, and they just keep getting better and better. So that's a nice thing, is you can just use all the research that's going into making those sort of state-of-the-art MIP solvers faster. You can do that, and so as a result, it's really often the best approach for many problems. Okay, so just keep that in mind. I'm going to tell you about other things, but don't forget this is the first thing you should always try. But there is a limitation. There's still a reason why I do research on this, is because, as I mentioned, these problems still just get enormous, right? If you have a base problem that's already pretty big, and then you multiply that by the number of scenarios that you have to consider, that might just be, ridiculously large, that there's not really much hope to even maybe solve LP relaxations of these problems. So you need to do something more. And so the general approach that, in the stochastic program that we try to do is something known as a decomposition algorithm. What we're going to try to do is take, this big problem and break it down into smaller problems. Okay, so solve a sequence of smaller problems and have an algorithmic strategy that brings that all together. And that's going to be, this Bender's cut approach that I'm going to be working on here. Okay. So how does this work? So Bender's decomposition. So let's consider this case here. So I'm going to have my first stage constraints here. I have this function QS, which is sort of recording the best response I can make if scenario S is what happens. I'm going to do a trick here right now, and I'm going to make a change in my model that I said, when I introduced this, at first I said the second stage problem might have integer variables. I'm going to sort of ignore that for now. I'm going to imagine the second stage problem only has continuous variables. It's a big change. It's a huge simplification. But there are methods that and some of the methods I'll talk about can handle, in certain ways, the integer case, but it's just kind of more complicated to describe that. And so I want to sort of just focus on this case. And so this case, what's very nice about this case is that this QS function is now the value function of a linear program, right? Where x are some parameters that show up in the right-hand side of that linear program in a fine way. And as a result, linear programming theory, it's not hard to sort of see that this function is piecewise linear convex in those first stage variables x. Okay, so that's sort of a nice property, and so now you can see this as being essentially a convex objective over mixed integer constraints in the first stage. Okay, so I won't get into the details of this, but it's important in implementing this that somehow, this is a convex function. You have to be able to, in order to have algorithms for that, you have to be able to evaluate that function and get sort of subgradients of that function. And that's done by solving this linear program and then using dual information. Okay, so the details don't matter, but just to understand that's the work that you do to do that. Okay, so how does this Bender's decomposition work? Is the first thing we're going to do is we'll start with our problem that I formulated on the previous slide. And the first thing I'm going to do is something kind of just silly, is I introduce a variable theta s for every scenario s that's going to represent the optimal cost of my recourse. And all I do is I just say, okay, theta s is greater than that function qs of x, right? Since I'm minimizing the ps's, these are probabilities, say they're 1 over s. Theta s is always going to equal qs of x, right? So this seems silly. I didn't really do anything here. But it's just a useful step to sort of derive, how we're going to algorithmically handle this. Okay. So this is sort of a trivial reformulation. But then what we're going to do is this qs of x, remember it's a convex function, but it's also piecewise linear, right? So it's defined as the maximum of a certain finite number of hyperplanes. And so the idea with Bender's decomposition is to kind of gradually build up a lower approximation of that. Okay, so that's the rough idea. And so what we'll do is we alternate between solving a main problem So where I have my first stage variables, I have those theta s variables that I want to represent the value function in each scenario s, my first stage constraints, and then don't worry about the notation of this. This is just saying these are a bunch of cuts that I've added to approximate, under approximate that value function as I go through the algorithm. So what I do is I solve that problem. I get a candidate solution, so that's, you can think of this as like a loop here. I solve that main problem, I get a candidate solution x hat, and I also have a theta hat, which is sort of, my guess of what the recourse value function might be for each scenario. And then what I do is I plug in that candidate solution x hat into the recourse problem, and I solve for every scenario totally independent of each other now. This is very important that it's a much smaller problem because it's a sequence of single scenario problems. Solve that problem, and from there I get potentially a Bender's cut that's going to sort of update my approximation of that piecewise linear convex function. So if that Bender's cut sort of cut off my theta hat, well then I have more work to do. If it didn't cut it off, then I know that I have sort of a good enough approximation and the problem solved. So that's the basic idea of this Bender's decomposition approach. And so as I've described this main problem is a mixed integer program, right? Every time I solve that main problem to get a new candidate solution, I'm enforcing integrality. So that solving that main problem is solving a mixed integer program, and that tends to be slow if you have to do this over and over again. So the real way that we sort of tend to implement this is you do kind of a single branch and bound search over the integer variables, and you add these cuts that you're deriving, they're called Bender's cuts, as needed in the branch and bound search. So I'm not going to bother to go into the details of that, but just to be clear that this is exactly how we do it, but some variants of that. Okay, so the key to success of this method is there are two keys, right? So first of all, remember we're working with this very, very big problem, lots of scenarios, so you have to be able to sort of process a node, a relaxation fast enough. And so that's where we need this decomposition. Right? So we want to always preserve this idea that, say, for a given first stage solution, I can solve subproblems for every different scenario separate from each other to keep that decomposition there. But the other thing is, with like any branch and bound algorithm, fundamentally it's still going to be branch and bound, we need to be able to sort of prune the branch and bound tree high up in the tree, right? So we need to be able to rule out sort of branches, and that's where we need strong relaxations. We need to have a relaxation that we solve at each sort of node in the search tree that sort of a good approximation of the true optimal value of that node. And so in this Bender's decomposition approach, that's a key challenge, is that if you just do the Bender's cuts as I described it, that LP relaxation that you're basically getting, that bound that you're getting, is often not very strong. And so that will lead to, okay, well fine, we can have decomposition, but the number of branch and bound nodes blows up and you sort of fail. Okay, so that's kind of a key challenge. So a general direction is to say, okay, well that's a problem, we need to get better cuts to improve those bounds, but this is complicated by the fact that we still have to remember this first thing. These cuts can't just be any cuts, they have to be cuts that can still be compatible with the decomposition method that we're using. So that's the crux of the challenge. Okay, any questions about that? So that's kind of the background of this branch and cut method and kind of the goal that we like to try to do. Yeah?
Can you say more about the compatibility condition?
Yeah, good question. So if I go back to the picture kind of illustrating this here. So ultimately, actually let me go all the way back to this extensive form. So ultimately, right, there's, you can think of this as this is a big mixed integer program, right? And so you could try to get any cuts in the world in this big mixed integer program. But notice the structure. You have these first stage variables of x, but then I have these ys variables that are like blocks. There's a different set of them for every scenario s. So as long as I derive cuts that only involve x and one block of ys variables, then I can still use Bender's decomposition. But if I derive cuts that mix x and one y-s for one scenario and the y-s is for another scenario and so on, then I can't do the Bender decomposition anymore. I'm not going to get this sort of breaking apart by scenario that I like to have in that method. So I'm really going to sort of want to focus on cuts that only interact x with the y-s variables one at a time. So that's good question. Other questions? Okay. So, I'm certainly not the first to work in this general field. As I mentioned, this is a general direction within stochastic integer programming. But the focus has typically been take cuts that are known for integer programming, which are somehow quick to generate, and adapt them so that you can apply them, in stochastic integer programming in this way. Right? So that's, there's been a lot of nice work along those lines. But, there's a couple of challenges with that. One is that, maybe those cuts just aren't that strong. And then the other thing is that it can be difficult maybe to implement, implementing all these things well is very hard, right? So the commercial solvers that do integer programming, they're really good at that, right? But if we're trying to do this on our own, you might not get all the sort of bells and whistles that they have, and so it's hard to get something that's working that well. So an alternative approach is to maybe think about just generating stronger cuts. And in this process of generating stronger cuts, the principle I want to think about is that I'm willing to solve a one scenario integer program in the process of generating a cut if it's going to give me a strong cut, right? So I'm willing to solve actually very hard problems like integer programs, as long as just one scenario at a time, right? Somehow if I want to be able to solve this stochastic integer program, I should expect that at least I can solve the deterministic version of that problem fast. So I'm taking that as a given and trying to see, okay, if we can do that, how much stronger of cuts can we get, and maybe how fast can we do that? Can we try to accelerate that? So I have two general directions, or sort of two different papers that Ray worked on that sort of do this for different structures of problems, and so I'll try to just mention these two in turn. Okay. So the first one is something called Lagrangian cuts. So it's a particular class of strong cuts. And so the basic idea of this goes back to a couple previous papers. But it really goes to what I just said. If I can solve to optimality a single scenario integer program, then by the equivalence of optimality and sort of separation, that tells me, okay, well, I can actually separate over the convex hull of single scenario integer program feasible set, and and get cuts that way. So that's the basic idea. If you are more like, if you like convex optimization, one way you can think of this is with you're looking at the conjugate of that value function. So that's this piecewise linear convex function. You can define the conjugate of this function for a given pi. You evaluate this conjugate function at pi as minimizing over, say, my first stage constraints. Kind of, you think of this as like I have a single scenario sort of value function, but then I add to that and modify it with the linear function pi transpose x, and then I minimize that. So it's a definition of this. Don't worry too much about that, except that just think about that solving this to evaluate this for a single pi. What I can do is just introduce the variables of the recourse decisions for that single scenario. And so I can evaluate Q star S of pi by solving a single scenario integer program. And that's the thing I said I'm willing to do. Okay, so that's the key thing to remember is it's not easy to evaluate this thing, but I can do it. Okay, and I'm willing to do it. So assuming that I'm able to do that, then you can define, it's sort of immediate by the definition, this thing that I call a Lagrangian cut, is if I fix some vector pi, and how to find the vector pi is a hard thing to do, so we'll talk about that in a minute, but for any fixed vector pi in Rn, then I get a valid inequality which says the pi transpose x plus the theta s is sort of my variable for representing that value function should be at least as large as the value of the conjugate function evaluated at pi. And this is nothing but the definition of the conjugate, right? I said qs star pi of x is the minimum of x of this expression, and theta is sort of meant to represent that function. So this must be greater equal to that by definition of what that quantity is. Okay, so there's nothing really magical about this cut. Okay, so that's all we're doing there. So then the question is how do I find it pi, right? So again, just to remember, notation for a fixed pi, this is what that thing means. And again, this amounts to solving a single scenario mixed integer program. This would give me this form of this Lagrangian cut. So then I can sort of think about finding a cut that cuts off a given candidate solution. So imagine I'm doing branch and bound, I've solved a relaxation, I get a relaxation solution x hat theta hat s, and so say generating Bender's cuts failed, right? I've done that as much as I could, now I want to generate a stronger cut. Then what I could do is try to find a pi that maximizes the violation of this cut. Okay, so I'm maximizing over those coefficients pi of basically the right-hand side minus the left-hand side of this cut. And so that's what we call the separation problem. Find that vector pi that sort of finds a cut that's most violent. And so this problem is, in fact, in some sense, nice because it's not hard to show that this pi, this conjugate function is a function of pi because it's the min of sort of, for every x, this is just a number, and that's in a linear function of pi. So it's the minimum of affine functions, and so it's piecewise linear concave. And so I'm maximizing this piecewise linear concave, and then this is just linear. So overall, I'm maximizing a piecewise linear concave function, which is sort of the easy way, and sort of, so it's convex optimization problem. And so, the thing is it's non-differentiable, so you might need something like the bundle method or something to kind of handle that. Okay, but the thing to remember, so that's the good news, but the bad news is remember, evaluating this and getting the super gradient that you might need to progress in these bundle methods involves solving that single scenario deterministic integer program. So it's something I'm willing to do, but I don't want to do it all that often, right? That's going to be quite slow if I have to do it too many times. Okay, so we want to try to speed this up. So this is kind of the general framework, and this is when I sort of cited other people have done this, people have tried this out before. And they found that these cuts are really good and strong, but it's very slow to generate them. So that's the kind of the goal, of this particular project was to just speed that up. So computational enhancements. Okay, so I have a list of 4 different things that we did that sort of incrementally contributed to that goal. So the first one is sort of a minor observation, but that actually ends up leading to a significant potential improvement that you can get without this observation. So the first thing that we do is, instead of looking at sort of that standard conjugate, we define kind of a modified conjugate. It's still a conjugate, but what we do is we sort of add additional variables. So pi are sort of the coefficients that are going to be in our cut in the end. And we add pi naught to be the coefficient on the recourse function. Right? Previously that was fixed at 1. All I've done now is say, okay, well, let's think of that also as a variable. It should be non-negative so things keep the right direction, but we just think of that as an additional variable. And then you can sort of derive the Lagrangian cut just as we did before, just by the definition of this. You can still write down, for any given pi and pi naught, this is a valid inequality if you can sort of just do this evaluation. And the important thing I want to emphasize is that this didn't really gain us anything in terms of the strength of cuts we might get from this method. You're still going to get the same family of cuts if you get all of them. But what hope it might gain for us is an improved efficiency of generating the cuts. Because what we can do now is reevaluate the definition of the cut separation problem. So now we're optimizing over the coefficients pi, but also this new pi naught that's going to sort of show up as the multiplier on the value function part. And then, that's sort of the constant term subtract these things for, again, the given x hat and theta has. The thing you notice about the objective is how it's homogeneous, right? So if I get a positive value on this objective, I can scale up pi and pi naught, and everything scales up. So without some other things I do on this, this would be either, the optimum value is either 0 or infinite, right? And this is sort of a typical thing that happens in, say, integer programming analysis. You have to then define some sort of normalization. So there's lots of different ways you can normalize that, and each different way you normalize so that you define sort of a concrete problem at that thing has a different impact in terms of which cut you select. right? So, as I said, I'm not changing the class of cuts that we're choosing from, but by doing this, we are now allowed to choose a normalization that might lead us to cuts that have more impact early on. So that's kind of the main idea here. And so, otherwise, the form of this is kind of the same as everything before. It's still going to be a convex optimization problem. Evaluating this is going to be a single scenario mixed integer program. So everything is the same except that we sort of are allowed to, we have more freedom in the choice of normalization, so that might allow us to get better cuts out of solving this. And this is similar to, in the context of just standard Bender's decomposition, Fischetti and co-authors sort of showed a nice way to sort of choose different cuts, and this is sort of inspired by that, but basically adapting these ideas to the Lagrangian context. And there's not a lot of theory you can say about, oh, this is better and you get faster convergence, but empirically it's been found that doing this and changing the normalization can have a very significant impact on performance, right? So it's a key parameter that you want to be able to explore as you try this out. Okay, so that's the first idea. The second idea, I think I'm going to skip this one because it's less significant and we are probably going to run out of time. So let me move on to the third idea. The third idea I think is really quite clever, and this was completely Rui. I mean, it was just like, he just came up with this video, I was like, I was a little skeptical, but it's like, okay, let's try it out. And so the idea is, so ultimately, there's this pi naught, but mainly, this vector of the pi coefficients. That's the thing we're optimizing over, and it could be a reasonably high dimension in terms of how many first-stage variables you have. So, in terms of solving this sort of convex, maximize a concave function optimization problem, it could be reasonably high dimensional, and then that's going to affect how many iterations you need to solve it. So his idea was to say, well, what if we constrain those coefficients to lie in the span of some coefficients of other cuts we've seen, right? And in this context, we have very natural candidate other cuts are these Bender's cuts, right, from just the LP relaxation. So we have certain other cuts that are hanging around, and what we say is, okay, we're no longer letting these coefficients be totally free. We constrain that they're, lie in the span of these other vectors that we fixate for error. And the effect of that is, so there's this parameter capital K is how many other vectors do we have? And basically, we've taken our, potentially high-dimensional optimization problem, and because of these constraints, really the only freedom is these lambda K variables, right? So that it's a much lower dimensional problem. And so you can hope that, and we've observed this, when you add these constraints, the number of iterations that you require before you sort of converge is much, much less, which means I'm solving many fewer of these deterministic mixed integer programs. Okay, so that's the motivation for this idea. Now, in this idea on its own, there's an inherent trade-off, right? I might want to have more of these basis vectors. Certainly if I have n of them, they span Rn, then I've recovered my original problem. I haven't done anything. But I would have strong cuts. But as I have fewer of them, and maybe they're not the right ones, I'm maybe going to miss something, right? So having more might be better. So there's a trade-off there. So the next idea we have is to think about, can we be more clever in thinking about which of those cuts we use in this sort of collection, right? So the idea here is imagine we have a pretty large family of past Bender's cuts, maybe more than we want to put into this problem because it wouldn't converge so fast. Can we somehow choose a good subset of them to use in that restricted cut separation? Okay, so that's sort of the final idea in this part here. So the idea is to go ahead and include them all in the model, but to add a restriction, sort of an L0 restriction on this, to say I'm only allowed to use capital K of them. Okay, so there's a typo here. This summation here, instead of K here, I should be summing over all of the possible IS. Okay, so this is summing over a large number of them potentially, but I'm only allowed a small number of them to be non-zero. Okay, so I have a large number of them, but I'm selecting a small number that I use. The first challenge in trying to do this, though, is this is an L0 constraint, right? So it's counting which ones are non-zero. And I'm in a program very happy to try to model, use binary variables to model a sparsity constraint. But to do that in this context, I need the lambda variables to have a finite upper bound, right? Otherwise, I need some kind of big M that I wouldn't know how to choose. So the first thing I'm going to do is I'm going to exploit the fact that we sort of homogenize the objective, and I can change my norm, right? The normalization I use is my choice, right? So the first thing I'm going to do is I'm going to change the normalization. Instead of normalizing by sort of the L1 norm on the coefficients of the cut, these new lambda variables that I have for choosing those weightings, I can put an L1 norm on those. Why not? It's still, you can sort of show that it's still going to capture the full family of possible cuts I might get. So I change my normalization. As soon as I have that change in my normalization, my lambda variables are now naturally bounded by 1, or plus or minus 1. Right? So now it's very easy to model that L0 restriction with some binary variables. I won't even bother to write it down, but you can probably see how you would do that. Okay, so that's good news. We can sort of write an integer programming formulation for this. But as I wrote this is still kind of a mixed integer nonlinear program, because this Q star of S, remember, is that piecewise linear concave function, right? So that's kind of, we probably don't want to do that just to generate a cut. So what we do is, one last sort of heuristic thing is we replace that Q star of S with whatever approximation we currently have. So as we're running this algorithm, we're getting Bender's cut, so we'll have some kind of approximation. We just go ahead and use that, and we don't worry about updating it. But then we solve this problem to sort of get a selection of which of these lambdas are going to be non-zero, and then we just use the associated pi k's as the selected ones, and then we go ahead and optimize the cut with that small set of those vectors in our span. Okay, so I'll just try to highlight a little bit, how this works. So we've looked at 2 test problems. So one's called stochastic server location problem, and then a stochastic network interdiction problem. So 2 different sort of stochastic integer programs. And what we're going to be looking at for this primarily is observing as time goes by and I'm generating cuts, how quickly does my bound improve? Right? Again, and the idea is that typically the way these cutting plane algorithms work is you generate cuts for a while and you get quick improvement, and then you just stop and you start doing branching bound. Okay, so it's important really that you get a lot of improvement quickly. It's less important that you improve to the best possible bound in the limit. Right? So that's what we want to look at. So what I'm going to show here is, in these sequence of the result slides here, is just one example instance of one problem class and one example instance of the other problem class. And you just have to take my word for it that these are fairly representative of the results you see overall. We have, of course, in the paper more broad results, but I just want to highlight things here. Okay, so I'm actually going to skip this one because that was the one I skipped earlier. So the first thing is to just think about this last idea in terms of the dimension k, in terms of this restriction that I do here. And so basically, what we see is kind of what you might expect. So let's look at this particular instance here. So let me first of all explain the figure here. So on the x-axis, this is solution time. So as the algorithm's running, we see what's happening. At the bottom here is a baseline, is the initial LP relaxation bound. So that's kind of like what you get before doing anything fancy. At the top here, that's the actual stochastic integer programming optimal value. That's the best case you could ever get to with these cuts. And as you add cuts, you hope that you bring the bound that you're getting up towards that. That's the goal. And so what we see is, as you sort of vary the number of sort of past cuts that you use in this restriction into this lower dimensional space, let's look, for example, at k equals 5, that's using a small number, I get pretty fast improvement, but then it stalls out, as you would expect, because I'm not using that many. For the other ones, you get sort of improvement to higher levels. And similarly here on this other instance, fast improvement, but you stall out. And so what we then did was this integer programming with the basis selection there. And what we see there is that as long as we're doing that basis selection, it doesn't really matter. So all of these different sort of results up here are basically different values of k, and they all work reasonably well. So the point of this is that with that integer programming for the basis selection, that parameter becomes less important, and so the overall algorithm is more robust, I guess. So the other thing in this specific example that I would show here is a comparison to basically kind of the state of the art before us. This is what's called BDD algorithm, sort of a heuristic method for generating these Lagrangian cuts. And so on this example instance here, what you see something interesting is it did pretty well right away, but then it had a portion of time when it was really stalled, and then it ended up doing okay, right? But we sort of skipped that stalled portion with this method. On this class of instance over here, that BDD algorithm was just very slow. So it took very long to improve the bounds, whereas these methods managed to improve it much more quickly. Okay, so I think I will maybe skip the remaining results and just say a few things about the other topics. So there was a second sort of general idea about how we might do this. And the second idea is related to a special case where we assume that the first stage variables x are all pure binary. Okay, so this is kind of restrictive, but it's still an important special case. And so in that special case, we have this kind of single scenario sort of value function set, right? I have my first stage variables, I have some constraints on them, and then I have my variable theta s. I want to be graded with this qs of x. So in terms of getting strong cuts that I can use within this Bender's decomposition framework, I'm trying to get strong inequalities for this set. Okay, so it's a specific mixed integer set. And if I think about the general mixed integer programming methodologies for getting strong valid inequalities, one technique that you can do is try to build kind of a union of polyhedra that covers your set. Okay, so this is like the main idea here. So the idea here, one way we're thinking about building such a union of polyhedra is we pick a subset of our first stage binary variables. Okay, so capital I is going to represent that subset. And then what I'm going to do is I'm going to enumerate over all possible values of that subvector of my variable. Okay, so these are the chi's. So given that subvector variables, I'm going to constrain my variables on that subvector to be equal to that specific choice. But the rest of it is just free, right? And notice here in particular, I'm relaxing instead of the x being binary. Now they're between 0 and 1. So this is like an LP relaxation. So for any fixed chi, that's sort of a selection of the values for that subset of variables. I plug this in. This is a certain polyhedron that I can sort of work with. Now, given a fixed subset of variables I, this is 2 to the cardinality of I polyhedron. So it's a large number. Certainly, as we think about this method, think about the cardinality of I as being like 5 or 10, not like 100 or something like that. Okay, so because these polyhedra cover my space, then if I can get valid inequality for the union of those polyhedra, that's going to be valid inequality for the set I'm interested in. Okay, so this goes back to the theory of Balish. He's described how you get valid inequalities for a union of polyhedra. And by doing it with these many terms like this, you might get very strong cuts. That's the motivation for this work. So how do you get cuts from having the union of many polyhedra? Well, Balish in his original work described a beautiful extended formulation, but this will not scale well if I have a lot of terms, like 2 to the cardinality of I terms, right? And even with just 2 terms, so cardinality of I is 1, it's kind of big, and so it doesn't scale well. And so usually when people try to generate cuts like this, they really are looking at just 1 term, or just 2 terms with cardinality of I is 1. In Balish and Perigard actually sort of considered some different ways to try to generate this cut that were certainly improvements over that, but still at most they would have like 2 to the 4 different terms. So it's hard to scale this up very, very large. So our idea was to kind of try to combine this idea of this multi-term disjunction with looking at sparse cuts. Okay, so what's a sparse cut? Sparse cut is just basically one of these inequalities we're looking for, but where the number of non-zeros showing up in the coefficients is small. Okay, so that's kind of a loose definition. Sparse cuts are nice because if you have sparse cuts and you're adding that to your LP relaxation, you can solve that LP relaxation pretty fast. So that's good to use them if you can. And there's some nice work by Shantanu Day and co-authors that sort of provided conditions when actually sparse cuts can approximate dense cuts pretty well. Under some conditions, they can't always, but sometimes they do. And so our idea was to, well, can we generate sparse multi-term destructive cuts effectively? Can we sort of combine these things? And then the basic idea, and this is where I'm really just going to summarize the idea at a very high level, is what we do is we combine these in a specific way. So what we say is we're going to ask for sparsity by restricting the support of the inequalities we're going to generate to be on the set capital I. And that set capital I is the same set that I'm using to define the multi-term disjunction, right? So there's that connection between those two that's significant and important. And by doing that, then what we can do is we can generate a value inequality in that space by solving one linear program for every term in the disjunction. So 2 to the cardinal A via linear programs. So again, it can't be huge, but maybe you can get to like 10 or 12. And then once you've collected data from each one of those linear programs, you build one linear program, solve that, and you get a valid cut. Right? So you don't have to iterate this process like you would have to do in the previous approaches, just to get one cut at the end of this. And so that kind of is seemed kind of nice. There's a bunch of challenges in terms of how do you choose that subset of variables, so we came up with some kind of computational heuristics to do that. But basically, I'll maybe just highlight this. I'll give 2 examples. So one example, on a test problem, you would expect this to work when there's somehow some natural sparsity in your problem. Okay, so this is an example problem where there is some natural sparsity already there, and so you could see, as you use smaller numbers of the cardinality of that set I that you enumerate over, let's say example 4, right? You get quick improvement, but then you tail off, right? Whereas if you use 10, you get slow improvement, but you get up to something higher. 100% would mean we closed all the gaps, so that would be really great. And then we had some adaptive version where you sort of start with small and sort of grow it only as needed, and that does this, kind of gets what you would want. But just to kind of show this doesn't always work so great, there's another class of instances that didn't have the natural sparsity, and in this one instance we could only close 30% of the gap. So it really depends on the structure of the instance whether you could expect this to work very well. Okay, so I'm going to wrap it up there. So hopefully I convinced you stochastic integer programming is an interesting problem class that models a lot of things, but it's still pretty hard to solve large-scale instances of it. But we're making a lot of progress. I think the branch and cut method is nice because it allows you to take advantage of the strengths of modern integer programming solvers, but we're going to need more work to generate cuts, strong cuts more quickly. And there's all kinds of other interesting things still to do here. I think a major issue is that there's a lot of different cool ideas for this, but integrating them all together into one, this is the way to solve stochastic integer programs, really requires a lot of engineering and selection of different things, and so that we sort of really don't have any good software that puts that all together very well. And so part of that would be identifying which cut generation strategy you should use. I presented 2 different ones, and they both seem to work pretty well on some instances, but which ones would you use on a given problem is tricky. And then I'm kind of quite interested in this idea of, so suppose you have a sequence of these problems to solve, for different samples, for example, how do you solve them more efficiently? I'll stop there. Thank
you. We have a couple of minutes for questions. Any questions?
I'm wondering if it's possible to solve the 3-stage or the k-stage version of this problem.
Yeah, that's a great question. So you can, this idea of 2-stage, you can easily imagine extending it to multiple stages. You recursively do this. It becomes, if you're talking about 3 stages, you can imagine kind of recursively doing that, and people certainly try that, and there's some hope to do that, I would say. But going to 10 stages or 12 stages, it just becomes really, really much more challenging, and I think you kind of need different approaches to build good approximations of such more dynamic problems. It's something I'm interested in and working on, but these methods maybe could be a tool in that, but you need other stuff to handle more than a couple stages. Yeah.
So does the problem become simpler if the stochasticity is only in the objective and not in the feasible region?
Yeah, so good question. So yeah, if it's only in the objective and its expected value, in fact, you can just plug in, compute the expected value and push it through, right? If it's a linear objective, it actually just becomes a deterministic problem. If it's a nonlinear objective, then then it comes back to this kind of challenge. But yeah, that's a big simplification in many cases.
You've pointed out this question of when to use one cut generation method versus another, but they're all valid. So can you just do both?
Certainly, I mean, yes, you can do both, but especially in the ones that I'm talking about here, they're expensive. right? So certainly, like, I gave that list of other ones that were all fast, like maybe you just try them all, right? But when these ones get to be more expensive, you want to really get to, you know, a stronger cut, you would like to have some sense in advance, is it going to be worth it to try that expensive generation? Yeah.
So then, sort of follow-on question, are you working to build either a intuition for when to use one or the other, or maybe some sort of machine learning clever thing to...
I'm not currently, but that would be great to do either of those things, right? Yeah, there's certainly future work to try to do either of those, yeah.
More questions? Okay, then, thank you, Jim.
Okay, good. Yeah, so to be on time. So there's, I mean,
Actually, I can tell it.
it's not very well done, I would say.
But like not
One of the things is on
it's like I launched it
set of variables go together. You know, so you have to, that's obvious that you're
Yeah, that's very strange.
after my meeting it.
But